All right, time for some more conversation about atoms and ionic bonds, referring again to our learning objectives. We want to know about things that are products when halogens react with metals and hydrogen, and we'll talk briefly also about the chemistry of noble gases. The halogens are the group 7A elements on the right side, next to the last column on the periodic table. Their properties are shown here in a chart. The one of most relevance to us is electron affinity. The electron affinity tells us that these elements, in a relative sense, are going to give off the most energy when electrons are gained. They gain electrons easily. This is described as being an oxidizing agent when they give up electrons to other atoms and compounds. That's what they're known for as halogens. They are seriously nonmetals, as you probably already figured out. They exist as diatomics in their elemental forms. We always show them as X2, whether it's fluorine, chlorine, bromine, iodine, or astatine, which is, of course, a very obscure element. It only occurs in very trace amounts anywhere. They are very reactive. Again, like their partners from the other side of the periodic table, they're very reactive, so they only occur in salts and in minerals in those kinds of places. Not very much ever found by themselves, but you can isolate them. And you can come up with these gaseous and other samples. So chlorine is, in fact, a gas in its naturally occurring form when it's pure. Bromine is a liquid when you find it. And that's what this little glass thing at the bottom is. We call it an ampule that's attached to a glass thing, but it vaporizes readily, so you can see the color of the bromine vapors in there. The bromine liquid is at the bottom, and this would be bromine vapors, bromine gas in the rest of that container. And the one on the right is iodine, which in fact is a solid. It also sublimes readily. It's the same thing that dry ice does. And so iodine as a solid is in the bottom, but there would be some iodine vapors in the top here. So that's kind of, each of these has characteristic colors. If you've ever heard about chlorine gas being around swimming pools, it's dangerous stuff. It's enough to send a person to the hospital. I spoke to the pool manager from Hislop, and he recounted an occurrence of a gas leak where he had to go to the hospital due to exposure to chlorine gas. It's very dangerous. Bromine has got a very nice reddish color in concentrated form. The bromine gas, you would not want to be exposed to that either. It's very reactive, not a good thing. And iodine is a solid. You've probably heard of iodine perhaps used as an antiseptic in treating wounds, but it's mixed in with another liquid to use it on your skin or someplace. All right, so the chemistry of the halogens, group 7A, has to do everything with their electron configuration, where they all have 2s electrons and p5 electrons, one short of having a full octet. And so they're going to gain that one electron for a full shell very readily, and that's how their chemistry can be explained. When they react with the metals, either the alkali metals or alkaline earth metals, plus a lot of other choices, you're going to get metal halides. Each of these are going to be with some number of halogens and some number of metals, depending on the charges of the metals. Any of those fluorine, chlorine, bromine, iodine halides will occur. And the other interesting thing that we've not described so far in other elements now is reactions with halogens and hydrogen. These would be hydrogen halides, and those are noteworthy because they end up creating things that we know of as acids. So things like HF, HCl, HBr, and HI, hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, are all acids. We'll get to talk about acids in another point, but that's something to notice at the moment. So each of those, you could balance the reactions and figure out how they work together, but we haven't delved into balancing so much at the moment, so let's not stress about that right now. Okay, so the interesting aspect to the group 7 elements compared to the alkali metals and alkaline earth metals is their difference in the direction for where the elements are the most reactive. The most reactive is fluorine. Fluorine at the top of the column is a very highly reactive element and makes it very difficult to get it pure. Notice that we didn't show an image of pure fluorine on that previous picture, but you can get samples of chlorine and bromine and iodine because they're not quite as reactive, and you can get them pure. So fluorine is very difficult to have pure. So the top of the column is the most reactive for the halogens. And so the increasing reactivity is the opposite direction on this end of the periodic table as it is for the metals. Remembering that they're going to gain 1 electron to make a full shell that resembles the nearest noble gas with 8 valence electrons. All right, so when they can react with hydrogen, what are we expecting here? Fill in our thoughts just one more to be clear. We're going to have the halogen gains an electron to become that -1 anion, and it's going to combine with hydrogen, which we can think of as having a +1 charge. We'll talk about that more too in the next chapter. Chapter 4, we'll have more discussion of those things. And these will occur indeed as gases, but we don't use them as gases. We'll put them into water and use them as in water solutions. All right, so the last part of the periodic table that we'll get some discussion here is the noble gases. Group 8A, the last column, otherwise known as Group 18. And we've probably heard about them now and then because these are the most stable elements. They're colorless and odorless. They're nonmetals. They're all gases. And they naturally occur that way, but they're terribly unreactive. They do not tend to lose or gain electrons either way. The ionization energies are very high, as we noted when we were describing those. And their abundance in air is variable, some of these far less than others. Apparently we would see neon more than we would see helium, but nobody's looking very hard. Argon is actually out there in air more than we think, and the other ones very, very small amounts ever. Very unreactive and not especially abundant. Their melting points and boiling points are so low that they're always gases. What else do we need to note about noble gases? Their names, interestingly, have some interesting derivations. I think word origins are kind of worthwhile at times. Helios is the origin of helium because it occurs in the sun. It's a Greek word. And neon comes from a Greek root meaning new, which seems kind of funny. If you've heard of neoclassicism or neo anything that means new, well, neon is like that. Argon means lazy, go figure. That's very funny. Kr for krypton means hidden. If you've ever heard of cryptographic informations or cryptograms, or those things are kind of hidden messages, and so that's what krypton is relating to. And xenon's name means strange. If you've ever heard of xenophobia, you're afraid of strangers or afraid of foreigners. So exactly what those root words sort of imply is exactly where their names comes from. Kind of funny, but oh well, a nice little trivia point for the day. The elements, the noble gases, when they're put in discharge tubes and given an electric current, they make colorful emissions, and these are reflected in those line spectra that we described back in chapter 2. Each of them has characteristic colors based on their electron configurations and where the transitions can occur between a stable ground state electron and an excited electron that has returned to its stable ground state. So you can think of signs that you've seen with neon and argon, perhaps. Krypton and xenon, probably not so often, but they're used in various scientific applications at times as well. All right, so what else to know about noble gases? Well, they're not very reactive. That's what noble is referring to. Sometimes they're referred to as inert gases in the sense that they don't do much. So if they're going to do anything at all, they're only going to do it under extreme conditions. You have to have either high temperature or high pressure to get the reaction to proceed, and even then, only certain elements within the noble gases react at all. So they're really only going to be with xenon, which, if you'll notice, is the last of the noble gases before you hit something radioactive. So the largest of the noble gases is the only one that has been forced into extreme chemistry with things like fluorine. Fluorine is terribly reactive, and the only thing you can get it to react with is xenon, probably not so much with krypton. I think there's some obscure or unusual examples with krypton, but not very many. So fluorine is very reactive, and so you can get it to make compounds with xenon, just as an interesting tidbit. Do we need to know about their formulas? Nope. We will look at their geometries and ratios eventually, but what you're not going to predict them. You will only describe the ones that are found. The compounds are known. There is a krypton example shown here, but they're mostly with fluorine, There's a couple of unusual ones with oxygen and xenon, but again, xenon is the most likely one to react because its electron cloud is larger and more able to be perturbed to form compounds. These are all really odd things, and so they're very obscure. They're just in a category of people have pushed the limits and found a way to make these things react. Okay, that was enough of the discussion of the elements from Group 7 and 8A. I hope these help you as you study.